Till now, we have studied about the wave nature of electromagnetic radiation, where we had seen that in electromagnetic radiation there are two components, electric and magnetic. And electric field and magnetic field are perpendicular to the direction of propagation of light. So this was the wave nature of electromagnetic radiation or wave nature of light. So in the wave nature we have studied about the electromagnetic spectrum, where we had seen that electromagnetic radiation has various components, that is the gamma rays, X-rays, UV, visible, infrared, microwaves, radio waves. There were various components. This was known as the electromagnetic spectrum, and they can be arranged in terms of frequency or in terms of wavelength. This was known as the wave nature of light. But later on there were some phenomenon like the black body radiation, the photoelectric effect or the atomic spectra, which were not explained by the wave nature of light. So later on, when photoelectric effect was discovered, Albert Einstein said that light is made up of tiny particles called photons, and each photon contains an energy of h nu, where nu is the frequency, that is called each quantum of energy. So this wave nature and particle nature both were present in light. So this was known as duality of properties. So light has dual nature. In some properties the wave nature is observed, and in some properties the particle nature is observed. So dual nature of light. One is the wave nature and another is the particle nature. But wave particle duality was still not proved exactly. So what were the conditions in which wave nature is observed? Wave nature is observed in some phenomenon like the interference and diffraction. All these properties was explained by the wave nature of light. And what did the particle nature explained? Particle nature explained phenomena like black body radiation, photoelectric effect, and atomic spectra. We have completed these two properties. Now atomic spectra is left. But before starting atomic spectra, we will see some numericals from the photoelectric effects. So let's start with this question. When electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 into 10 to the power 5 joule per mole. What is the minimum energy needed to remove an electron from sodium? What is the maximum wavelength that will cause a photoelectron to be emitted? So these are the questions. First of all, photoelectron is actually electron emitted by light. Means the electron emitted due to photoelectric effect is called photoelectron. So here what we are given with, we have the wavelength, we have kinetic energy. These are given. So what we are given with, wavelength and kinetic energy. And what we need to find out, minimum energy needed to remove an electron from sodium. What is the minimum energy needed to remove an electron? That is the work function. Work function. Then maximum wavelength, that is lambda naught. Okay. So first of all, we are given with lambda, that is 300 nanometer. If we convert it into SI unit, it will be 300 into 10 to the power minus 9 meters. Now we know that energy is equal to work function plus kinetic energy. So we need to find out work function. Kinetic energy is given. So we need E now. How will we find out E? If we have the wavelength, E equal to h nu, right? We don't have the frequency, we have the wavelength. So how can we write it in terms of wavelength? We can write hc by lambda, because nu equal to c by lambda. So this will come as, value of h is 6.626 into 10 to the power minus 34 joule second into 3 into 10 to the power 8 meter per second by 300. Actually 300 into 10 to the power minus 9. How can we write this like? We can write 3 into 10 to the power minus 7 meters. So 3 into 10 to the power minus 7 meters. So second and second inverse is cancelled. Meter and meter is cancelled. We know the unit of energy is joule. So we are getting joule. Now the calculation. 3 and 3 will also get cancelled. So we have E equal to 6.626 into 10 to the power minus 34 plus 8 plus 7. So it will be 6.626 into 10 to the power minus 19 joule. This is the energy. Now, one interesting thing is the kinetic energy is given in joule per mole, but we have energy in joule. We cannot calculate, we cannot add or subtract two different units. We need to convert it into the same unit. So, if this is the energy for single photon, then what will be the energy for 1 mole of photon? Energy for 1 mole of photon. Let's consider this as EM. So, EM will be equal to E into 6.022 into 10 to the power 23 mole inverse. So, what is the value of energy here? Value of energy is this. So, 6.626 into 10 to the power minus 19 joules into 6.022 into 10 to the power 23 mole inverse. So, we will have 3.99 into 10 to the power 5 joule per mole. So, we have got energy in terms of mole. Now, work function is equal to total energy minus kinetic energy. So, we get 3.99 into 10 to the power 5 joule per mole minus, what is kinetic energy? 1.68 into 10 to the power 5. 1.68 into 10 to the power 5 joule per mole. So, if we take 10 to the power 5 as common, 3.99 minus 1.68 into 10 to the power 5 joule per mole. So, this will come as 2.31 into 10 to the power 5 joule per mole. Now, we have received this in joule per mole, but the question said minimum energy needed to remove an electron from sodium. They didn't say 1 mole of electron. So, if 1 photon corresponds to 1 electron ejection, then 1 mole of photon will correspond to the ejection of 1 mole of electrons. But in the question, we need the energy to eject 1 electron. So, we need to convert this back into joule. So, now we have, let's consider this at this, equal to 2.31 into 10 to the power 5 joule plus mole. So, what will be the work function? That is the minimum energy to eject 1 electron. This will be by 6.022 into 10 to the power 23 mole inverse. Okay, so this is 2.31 into 10 to the power 5 joule per mole by 6.022 into 10 to the power 23 mole inverse. So mole inverse and mole inverse is cancelled. So we get 3.84 into 10 to the power minus 19 joules. This is the work function. Now the second question was maximum wavelength that will cause a photoelectron to be emitted. What will be the maximum wavelength? If lambda naught is the maximum wavelength, then lambda naught is equal to C by nu naught. How will we get nu naught? Nu naught will be equal to work function by h, since work function is equal to h nu naught. So we have work function, now nu naught equal to 3.84 into 10 to the power minus 19 joule by 6.626 into 10 to the power minus 34 joule second. We cancel out joules and we get nu naught is this. So if we directly put the value, lambda naught is equal to C by nu naught. So what will be the value of lambda naught? Lambda naught is equal to, it will be CH by work function, right? So this will come as 3 into 10 to the power 8 meter per second into 6.626 into 10 to the power minus 34 joule second by 3.84 into 10 to the power minus 19 joules. Okay, so we cancel out joule and we cancel out second and second inverse. So we get 5.17 into 10 to the power minus 7 meters. Now if we, so it can be written as 517 into 10 to the power minus 9 meters. So 517 nanometer. This is the lambda max. Okay, so we have got two answers. We have the work function as 3.84 into 10 to the power minus 19 joule, and we have the lambda max equal to 517 nanometer. So next we will see further numericals. Thank you.